Hi again. So let's talk about one more thing before we get into our inference, okay? The last thing is r squared, or the coefficient of determination. This is the thing I mentioned earlier that is a percentage, and this is also only applies to linear models, okay? Which we are only doing in this class. But just so you know, any mathematical formula, like a quadratic, parabola, exponential, anything that you have an equation for, you can do linear regression. Or sorry, it wouldn't be linear. You can do regression on any linear or non-linear model, okay? And so you might take a whole class on that. You can also do multivariable regression, which this is just a single variable, x, and then to predict y. Okay, so r squared, it is literally r squared, the correlation coefficient squared, okay? I'm not sure why they use a capital R instead of the lowercase r, or you could just think of it as the correlation squared, the correlation coefficient squared, okay? But it has a different interpretation. You might know when you square a number, even if it's negative, it's going to turn positive, right? So it's going to be a positive number, and we interpret as the percentage of variation in the y variable. So we insert context here. What is the y variable? The percentage of variation in the y variable that can be explained by the x variable. Okay, so we're going to describe this for our data set using those variables, okay? So first of all, let's go back to our regression output and see where that is located. In our regular regression output, it gives us r squared. And one other thing I want to just highlight in this applet, because it can be a little confusing, is there's a separate button for least squares regression line. So line is linear. Then down below it says calculate other regression models, where you have quadratic and exponential options, but we're not going to use any of those. Sometimes people jump down here and skip over this one and end up with a curve, but we want to go to the very first button and do the least squares regression line. So that's the linear. Other programs would have just linear, quadratic, exponential, and other options all in the same menu, so that's what might be a little confusing. Okay, so here's our r correlation, negative about 0.5, 5 squared is 25, and this is 0.2486. So what I want to show you is that it is actually the correlation squared. So I'm going to put in my calculator, and then I'll show you, but I want to enter so I can see this number, negative 0.4986. Okay, let me go back to the notes. And I put it in parentheses because to square a negative, we need the negative times itself, right? If I don't put the parentheses in there, it will still be negative. Okay, so I square it, I get 0.2486. I believe that is what it said, 2486, okay? So you can also just take your r and square it, or if you have r squared, you can take the square root to get r, but then you got to figure out the sign as well. So there are lots of relationships here. So let's write this down. R squared equals 0.2486. Right, 6, which means now I'm going to turn it into a percentage. 24.86%. So it's the percent of the variation. Percent of the variation. And we're still talking about the financial aid award at this college, Elmhurst University, of the variation in the y variable. So in the award amount, okay, that can be explained by, therefore is the amount, means 24.86 of the variation in the award amount can be explained by, get my grammar, can be explained by the variation in family income. I'm just going to remind us of the cases of the student. Okay, so remember the X values are varying, right? Student to student or family to family. And then the Y values are also varying, okay? So this is taking all that into account. It's saying 24.86% of the variation in the award amount, the Y values, can be explained by the variation in the family income of the student, the X values. Now, the rest, why do we want to know this? Well, that means the rest is due to other factors, okay? So this kind of gives us a sense. Well, is income, 80% in determining the award amount? Here it's only about a quarter, so that means there's other factors that are coming into play. So I'm going to say the rest, and I'm just going to calculate that as 100% minus 24.86%. So let's do that. 75.14% is due to other factors. Okay, now we might think about for a second, what are some other factors that might contribute here? What might other factors be in this case? Or some other things you think universities might take into account. Maybe they're taking into account things like GPA or SAT, ACT scores. Okay, maybe they're taking into account race and ethnicity. So we've already got family income, maybe community service, other like volunteer community service. I'll say service, maybe someone's essay has an impact on that. So there could be lots of other things that are taken into account for a financial aid award package, okay? And if you do more on regression specifically, you can do multivariable. So you can actually have more, you can have your Y column and you can have several X columns, and it's super interesting. They all have to be quantitative though, so that is a little bit tricky. We couldn't do it with a categorical, but we could do it with GPA or SAT or ACT scores. So that would be really interesting to do too. Okay, so there's more you can do on this, way more. Okay, let's switch over now to inference. We got a little bit of a start on it, talking about the residuals. So we talked about the residuals following a normal distribution, but for inference, just like with means, we use a t-distribution. But we know the t-distribution with high enough degrees of freedom becomes a normal distribution. Okay, so let's look at what conditions we need and what our model is going to be. So let me just uncover all these. Some of these will look familiar and some might be new. Okay, so linearity. So that is a new one specifically for this. Check the scatter plot for a linear pattern, okay? Just like everything we're doing in this class, we're only talking about linear patterns, okay? Now, independence, that one's very familiar to you. The observations are independent of each other, okay? And we could say in terms of the X and Y, yeah, I think we would need X and Y. We definitely want to be careful of time series plots, okay? So sometimes we have one of the variables X is time, has to be the independent variable. Got to be careful of time because maybe there's something else going on. Like let's say you did exercise over time, or other, yeah, just be careful of time series plots. Randomization. The data should be from a random sample or a randomized experiment. Okay, so here we have a random sample of 50 students from this college, which leaves us a sample size and nearly normal residuals. Okay, so we're used to a sample size with means checking, or at least with numerical variables, checking for nearly normal, right? So this is very similar to that. N has to be greater than or equal to 30, or check the residual dot plot for nearly normal residuals, okay? Now another new one, constant variability of the residuals. I mentioned this before with the residual plot. We don't want to see any patterns, okay? So what we're going to do is check the residual scatter plot to make sure there are no obvious patterns, okay? Now what do I mean by that? Let me, I kind of explained it before, but let me actually draw it out. So here's our residual plot with 0. Remember 0 is the regression line now, and we want just even scatter, right? Just evenly scattered around that, that 0 line, okay? We don't want to see something like a V pattern, like something going up or down, where there's a pattern in that there's very little variability, and then there's, for some reason, this could be an issue with time series plots, like maybe there's not very much variability in the earlier years, but then there's a ton of variability in the later years. So you don't want this, this would not be constant variability, right? This would be changing variability. It could also go the other way, or it could go up and down, you know, but I'm just going to draw the kind of two extremes. Maybe there's a lot of variability in the early, in whatever the lower x values are, and then not much variability. Okay, so these two are bad. This one is good. We want no obvious patterns, okay? Constant variability. Okay, so that's one of our conditions for inference. Now, when we get ready to do inference, our degrees of freedom are n minus 2. Okay, so I mentioned that, and it's -1 for the x, because you know you're used to -1, right? -1 for the y variable. Okay, now let's get to the hypotheses. Okay, so we are going to do hypothesis testing in terms of the slope. Now, this can be framed in either the slope or the correlation, okay? But they are very similar to each other, okay? So if we're saying the slope, so slope was our beta, that was our population slope. Let me go back to that page real quick. So here in our population line, and remember, so let's say we have this one sample, right? We have this one sample, 50 students, we have a line, but what if we took a different sample, and a different sample, and a different sample? These would all be different, right? And we're trying to estimate the population slope, okay? So if the population slope is 0, that means there's no real trend in the population. Okay, and any apparent trend is just due to data selection by chance. So it's just due to that particular sample we got, okay? So this would be very similar to doing R equals 0, which would also mean no trend in the population. But if you have a 0 correlation, 0 slope, they kind of mean the same. They're very similar ideas, okay? So some textbooks use slope, some textbooks use correlation. So we're using slope because that's what Staplet does. Okay, so beta equals 0, slope 0, no real trend in the population. So our claim, or alternative, we've got our three usual possibilities. Either two-sided, it's not 0, or it's positive, or it's negative. Okay, greater than 0 or less than 0. And that would be saying there is a real trend in the population. Okay, so then our observed statistic, our test statistic is a t-score, because we're using that t-distribution. If we have all these conditions met, we are going to do this theoretically and not a simulation. There are some simulations you can do, but we're going to stick with theoretical for this one. So our t-test statistic, our t-statistic, this is called a t-test for the slope, is our observed statistic. So it's our slope minus the null value, which is always going to be 0 in this case, over the standard error of the estimate, or SE. Okay, so this is where we do need that sample-to-sample variation, right? We have to get an estimate of that, and I'll show you where we get that in Staplet, okay? So, and then we can also do a confidence interval for the slope. So this would be our point estimate, B, our sample slope, plus or minus the t degrees of freedom times t star with the degrees of freedom times the standard error. So just like the usual formula you're used to using, but just we're using slope now instead of x bar or p hat. Okay, great. So I think I'll continue. We're going to check the conditions and then go into the rest of the analysis with Staplet. So let's switch over to the next video to start that. Okay, I'll see you over there.